I'm going to be talking through the topic a bit, through the problems, what we've learned from looking at those problems. Overall, I'd say the problems went really well, so I don't feel the need to talk over every single one in great detail. I feel like a lot of them, you all got the right answers. So I am going to go through a few of them, especially with regards to kind of the concepts that have come up and what equations are especially relevant and how this connects into other problems or more general applications. During my little spiel here, which I think will probably last around 30, 40 minutes, if you have questions, you can ask them in the chat. Alyssa, or one of our peer facilitators, will take a look at the chat. If it's a quick thing and she can answer it, she'll answer it. If she thinks it's something I should answer, she'll hold off, and then when we're all done, she'll remind me of the chat questions, and I'll take a look at those. Alyssa's also doing us the service of just kind of moderating everything. I don't foresee a problem, but just in case, we have some moderation. And yeah, the whole session is recorded. The video and the slides themselves, independent of the video, will be posted up. And that's going to be true every week. Okay, so for our first unit, right, we have been looking at simple harmonic oscillators. And so here are the learning outcomes that we had up on the first assignment in that module. The idea behind simple harmonic oscillators is we're not just talking about, say, like a mass and a spring. Like, as cool as a mass and a spring is, it's one system, right? We don't need to spend a whole week talking about how to solve for the equations of motion for just like a mass and a spring, you know, especially because it builds on a lot of stuff from 121 that ostensibly we already know. So really, the idea behind a simple harmonic oscillator is it's an entire class of system, and we can look at examples like a pendulum or a mass on a spring and figure out how to characterize an entire class of systems. And if you go on into mechanical engineering, civil engineering, or physics, you realize that this class of system is a really great approximation for loads of different things. So by figuring out how this system works, we have an approximate model for tons and tons of different mechanical systems that we can get into. So the main thing we want to be able to do with simple harmonic oscillators is we want to identify what makes a simple harmonic oscillator, right? It's not just this oscillation back and forth, but what makes it a simple harmonic? There's a certain relationship between the force and the position, and that leads to some special properties of how the equation of motion looks. We also want to make serious use of conservation of energy where possible to kind of work our way through some of these problems. And we want to identify how we can connect the physical properties of the system to the equations of motion for the oscillator. And like I said, we want to do this as generally as possible so we can start applying this stuff to other systems. Quick sidebar. So as we work on problems, it's important, right, in here not just to give your answer, right, but also to show how you got your answer. Especially with those first tier, like low stakes problems that you've been working on so far, right? Those aren't even graded on correctness because, right, it isn't really fair for me to say, hey, you know all your physics, right, before we've even kind of talked about it or worked on it together. So I really want to see from those problems a sense of like how you're approaching the problem and what you tried. So these up here are some example problem solving guidelines. These also are really great to do if you feel really stuck on a problem. For me, like, sketching is always super important. And it's not just like, oh, we're in, you know, first level physics, so sketches. Like, sketches stay important all through physics. Like, even for like graduate level physics, like a sketch of a problem or a system is really, really useful. Just flagging like all the variables you know and writing them down just so you don't have to keep them in your head. Listing out equations, right? Oftentimes you might need more than one equation to solve a problem. And sometimes you'll be able to like make the link in your head like, oh, okay, I know I have this, so I know I need to use these 3 equations or whatever. But more often you won't be able to, and then that's when you really get stuck. So writing down equations that might help, like, don't wait until you're sure you know what to do. just take a few, like when you think of an equation that might help, just write it down so that you can use the paper or use whatever's in front of you as a tool rather than just trying to keep a bunch of equations straight in your head and trying to connect the dots. Or just putting out equations and concepts that might be helpful are great. Okay, and I also recommend like if plugging in numbers as the very last thing that you do. Oftentimes when you're using more than one equation, like doing some algebra or combining equations just makes things go a lot smoother before you put numbers in. So those are just some kind of like general problem solving guidelines. Okay, so one of the first problems I asked had to do with drawing a free body diagram for a mass and a spring. And this is kind of like a refresh for mechanics, but also a great way of introducing like what makes a simple harmonic oscillator special. So, right, the idea behind a free body diagram is we draw arrows corresponding to forces. Every force is on something by something. So everything on the free body diagram is acting on the box. So we've got an upward force from the spring and a downward force from gravity. And we can relate those to the distance the spring has stretched. So if I write down Newton's second law here and say my net force is the mass times the acceleration, which in turn is given by the sum of these two forces, then I get that the acceleration is going to depend on the distance. I can even do a little substitution where I write, I invent a new variable, x prime, that's like the amount extra that the spring is stretched from its new hanging equilibrium position, if I want to make this really obvious. But the thing we're really interested in when we look at this is that acceleration we know is the second derivative of position, and the acceleration depends on the position. So basically, whether we're ready for it or not, we've got a differential equation here. So if you've taken differential equations, then you know, right, there might be some strategies that we can use here that might help. But most of us probably haven't taken differential equations. So rather than worrying about solving that, we can just think of what kind of functions might work here. So if I'm looking for the second derivative of a function gives me a negative sign times the function, this is going to give us sines or cosines. And so this is how we arrive at this kind of functional form for the equation of motion for a simple harmonic oscillator. So a cosine, right, if I take two derivatives, I get back a cosine with a negative sign. So it's going to work in this equation. Speaking really generally, and so generally it's not even necessarily super helpful, right? Any simple harmonic oscillator is something that obeys this differential equation, where the second derivative of position is negative something times the position. Another way to put this would be the force is dependent on the distance from some sort of equilibrium. So in the case of a mass and a spring, then the force is dependent on how far I shift the mass up or down. For a pendulum, the force, the restoring torque is dependent on the angle. I'm literally making hand gestures as if you can see me, but like I don't have a camera turned on, so I'm not sure why I'm doing that. So every simple harmonic oscillator has a similar equation that it obeys. Something like the acceleration is negative something times the position. The something is what we call omega squared, where omega is the angular frequency. So what exactly the angular frequency is depends on the system. So this is the part of the problem that's going to be different whether we're looking at a spring or a pendulum or another system entirely. So for a spring, omega is given by the square root of k over m. So k is the spring constant and m is the mass that's hanging from the spring. For a pendulum, omega is going to be something different, right? For a physical pendulum, like a hula hoop, it's going to be different than that. For oscillating circuits, it's going to be something else entirely. But all of those systems are going to be related to this same differential equation. So that's what all of these systems have in common from just like a really high level kind of perspective. So this angular frequency, right, we can relate it to things we might be more comfortable with, like the period or the conventional frequency. So the period is the time it takes for the system to oscillate a full loop back to where it started. And so that's related to the angular frequency 2 pi over omega. And the conventional frequency is the number of oscillations per second, and it's just 1 over the period, or omega over, or sorry, omega over 2 pi. Okay, so talking about the next problem, and like I said, I say next problem, I'm not actually covering every single problem. I'm going to skip over a few because we had a really high rate of everybody getting pretty solid answers on all of these. So the next one I want to talk about is the properties of simple harmonic motion, where I had you plot the velocity and the position as a function of time for a spring oscillator. So this was the plot that I arrived at. So the position looks something like a cosine function. The velocity looks something like a negative sine function. And we can identify certain times that are really interesting to us. So at time 0, we can identify that the velocity is going to be 0 and the position is far from the equilibrium. If I go to a time that's a quarter of the period, that's going to be where the position curve crosses 0. So that's where the object gets back to equilibrium. And I can see that at that moment, the velocity is far from 0. So I'm going to be able to put something together in terms of when the position is far from equilibrium, the velocity is going to be small. When the position is at equilibrium, the velocity is going to be large. And this is going to be something I want to connect to energy relatively quickly. So for energy, I wanted us to think about plotting the energy as a function of position, which is a little bit weird, given that we were just talking about plotting something in terms of time. So if I want to plot the energy in terms of position, I need to remember the potential energy of the spring being 1/2 kx squared. So I can plot that. That's just like a parabola. And I see that I have the maximum potential energy when I have my maximum x. So when do I have my maximum x? Well, I can go back to the curve I drew before. That's going to be at time 0, half the period, 3/4 of the, or 3/2 the period, and so on and so forth. So every half period, I arrive at one of these positions. So in terms of what the maximum potential energy is, that depends on how far away I get from equilibrium. So that's where this amplitude comes in. So the amplitude tells me how far up the curve I get. And so if I plug in x is equal to the amplitude, that'll give me the maximum potential energy. So figure out the kinetic energy, that's a little bit trickier to graph as a function of position. So I want to make use of the idea that without friction, right, the total energy is going to be conserved. So if I imagine that the total energy is the same as time goes by, that means whatever I draw for my kinetic energy, if I do potential energy plus kinetic energy, right, I should always be up at the total amount of energy. So that means my kinetic energy curve has to be at its maximum when my potential is 0, and my kinetic energy curve should go to 0 when my potential energy is at its maximum. So because the equation I have for kinetic energy looks like 1/2 mv squared, then I know my biggest velocity is going to be at x equals 0. So I can come up with some really useful conservation of energy equations. So my total energy, right, is given by kinetic plus potential. So that's going to be equal to like 1/2 mv squared plus 1/2 kx squared. So I could plug in any velocity that my system could have and use this equation to figure out what the x would be at that velocity if I knew the total energy. So maybe I know the total energy, and then if I know the velocity or the position, I could find the other one. If I am looking for like the maximum velocity or the amplitude, then finding the total energy is also a good idea, because the total energy is going to be equal to the maximum kinetic energy or the maximum potential energy. Because keep in mind, I'm trading this energy back and forth as I move, and then I have the same total amount of energy. So when I have a position where all my energy is potential energy, that might be a useful moment to calculate my total energy, and I can set that equal to my maximum kinetic energy. If I'm at a position where neither my kinetic nor my potential energy is 0, then I've got to use this form here, where I'm keeping track of both the position and the velocity to find the total energy. Okay, so like I said, this stuff doesn't just apply to masses hanging on springs. So the next system I had you all look at was the pendulum. And so trying to remember an equation for torque. So there's lots of different ways we could think about torque. I think about it as like R cross F, right? So when I think about R cross F, I have the magnitude of R times the magnitude of F times the sine of the angle between those two things. So the magnitude of the torque in this case would be mgl times sine of theta. And the direction of torque gets a little bit tricky. We probably want to think about a right-hand rule or something like that. But ultimately, what I really care about is that the direction of torque is a restoring torque, right? So if I pull this mass, this bob away from the center line, the torque is going to act to move it back towards center. So if I write down this equation in that kind of differential equation form we were looking at before, I get that the moment of inertia times the angular acceleration is negative mg times the distance to the center of mass times sine of theta. So this is a problem. We're not very practiced at solving differential equations, but even if we were, this differential equation has no solution. There's no function I can put in where the second derivative of the function with respect to time is always the sine of theta. You have to come up with like a numerical solution for that. We really don't. It's not just like we're not good enough to come up with a solution to that differential equation. There isn't one. You have to solve this equation numerically. There's no analytical function that solves the net torque is equal to sine of theta for any value of theta. So we can't get a theta versus time function out of that. So this is what motivates us to take the small angle approximation, because that gives us this more doable equation where we can think about, okay, if theta is small, right? If theta is like much less than 1 radian, then I'm in good shape. If I need a more specific or more precise indication of like when this approximation is good enough, then I can take a Taylor series and look at the higher terms. But that's, I mean, almost certainly overkill for what we're doing in here. But if you really care about like, I got to know how good my approximation is, then we would think about the Taylor series. So what's kind of nice about the pendulum equation is it works for all sorts of stuff that doesn't look like a typical pendulum. So if we imagine like hanging a wrench from a peg or some kind of weirdly shaped object hanging from a single peg, we can find frequencies of oscillations about small angles. And what we care about for this equation is we would need to know the moment of inertia of the object about its pivot point, and we would need to know where the center of mass was. If we know those things, then we can throw those into the equation for our physical pendulum. So the hula hoop questions kind of got at that a little bit, where the center of mass was the center of the hoop. And I could look up the moment of inertia for a hoop about its edge. And looking up moments of inertia is fine where we can. Calculating a moment of inertia from scratch is a little bit outside what we would need to do, for sure. So when I talk about pendulums, probably most of us think about the simple pendulum, which is that like heavy bob at the end of a massless rigid rod. So for this case, right, the distance to the center of mass would be the same thing as the length of the pendulum rod. And the moment of inertia would just be given by the moment of inertia for a point mass. So I can plug in ml squared for the moment of inertia. I can plug in the length of the pendulum for the distance to the center of mass. And I arrive at, right, the second derivative of theta with respect to time is negative g over L times theta. So now we have an equation that looks, right, just like the equation we had for the mass in the spring, meaning that this is going to be a simple harmonic oscillator as well. And we can come up with an expression for omega, right? Where in this case, omega is going to be something like the square root of g over L. So in this case, my equations of motion, instead of being like x versus time and velocity versus time, they're going to be like angle versus time and angular velocity versus time. So something I should point out here, because this is probably going to confuse all of us at some point or another, is I've written out the angular velocity as like theta with a dot on it, which may or may not be something that we're like super familiar with. But I need to do that because omega is being used for something else, right? Omega is what we're using for angular frequency, whereas in a previous quarter, we might have used omega for angular velocity. So theta dot would be something like radians per second, right? In the sense of like, I'm changing my angle position in radians every second, whereas omega is, right, has to do with the rate at which we are oscillating as an oscillator. So omega is not the same thing as angular velocity in this unit. So that might get a little bit confusing. It's going to be like you have a pendulum and then not draw you a picture and then like need you to guess that it's like actually shaped like a wrench or something. So I feel like if it's a problem for me, I'll probably just say a simple pendulum. Whereas like a physical pendulum would be, I might not say physical pendulum, I might describe the object that's behaving as a pendulum if I was writing the problem.
Mm-hmm.
Okay, so based on that, right, that's how we figure out quantitatively what's going on with the pendulum, right? The angular frequency was that square root of g over L. So using that, we can find the period. Writing out the equations of motion, right? The amplitude would be something like the maximum angle. And the amplitude for the velocity would be, right, omega times the amplitude, which like I said, is going to be like an angular velocity. So one way we could think about that might be like the maximum velocity over the radius or the maximum velocity over the length of the pendulum, right? So if we're thinking about like an angular velocity, if we take a linear velocity and divide by the radius, like we did when we were doing circular motion way back in 121, right? That's how we got something that had the units of angular velocity. So the position where I'm at my maximum speed conceptually is very similar to what was going on before, where when my position is at equilibrium, so in this case, when my angle is 0, I'm at my maximum velocity. I'm at my maximum amplitude when my velocity is 0. So conceptually, we have something very similar to what was going on before, where I'm going to be trading back and forth between kinetic and potential energy as this thing oscillates. So there are going to be moments where all my energy is kinetic energy and other moments where all my energy is potential energy. So based on that, I can find the total amount of energy, and then that's going to be really useful. In this case, the potential energy that I have is going to be related to the bob reaching a certain height. So one way I could write that might be useful is to write the potential energy as the mass of the bob times g times the height. So if I find the maximum kinetic energy, right, then I can set that equal to the total energy, and I can set the total energy equal to the maximum potential energy. If I do that and I rearrange it to find height, I get that the maximum height is going to be the maximum velocity squared over 2g, which gives me something about like 0.2 meters. So the last part of this problem is a little bit tricky to figure out what angle this corresponds to. And this is just like kind of a fun geometry problem for a certain definition of fun. So the way I like to visualize it is I draw this picture with, right, the height, right, being something that I know. So that's the difference in the position of the bob at equilibrium versus the position of the bob at an angle theta. I can do some trigonometry. I know the length of the pendulum, right? I've kind of exaggerated this part here, but I know the length of the pendulum arm. So that's going to be L. And so this guy over here is going to be L cosine theta. And I can relate that looking for height is going to be the difference between the length of the pendulum and that L cosine theta. L cosine theta, I can then solve for by, right, in terms of H and L. And if I do that carefully in this problem, I end up with an angle of 0.368 radians. So again, this is really just a case where drawing a picture is just really useful. And there's going to be no shortage of cases where drawing pictures is really useful. So that's just going to be something we want to keep in mind. Like when we can draw a picture, we should draw a picture. Okay, so the last few problems I want to talk about are all just kind of related to some of the simple harmonic oscillator concepts. So for example, if I have a swinging pendulum and I know its amplitude, and then I give it a little tap as it swings by that slows it down, what I have done is I have changed its energy, right? So now I have less energy in the system. So anything that's related to energy is going to change. So amplitude, total energy, and maximum velocity are all going to change because I've changed the energy of the system. What's not going to change is the period. So the period doesn't depend on the amplitude, it doesn't depend on the velocity, it doesn't depend on the energy. It's just given by the physical properties of the oscillator, in this case, the length of the pendulum and G. So on one hand, that's fairly straightforward. On the other hand, it's really weird, right? The idea that the period has no dependence on how fast the object is moving is not a super intuitive bit of superharmonic oscillators, right? So the idea, if I pull this oscillator out to 1 degree versus pulling it out to 5 degrees, it's going to oscillate with the same period, right? That's a fundamental part of how an oscillator works, but certainly not a super intuitive one. In terms of the net force and the velocity vector, this is one that's nice to draw out in a few different ways. Basically, if you can find a counter example to one of these, then you know which one is wrong. And so in this case, it's the net force opposing the velocity vector that's incorrect, because I can find a moment where the net force on the pendulum bob and its velocity are in the same direction. So once I have that moment, I know that sometimes the force is going the same direction as the velocity, which is an equivalent statement to saying sometimes the pendulum is speeding up, right? It's not always slowing down. Sometimes it's speeding up, sometimes it's slowing down. So in terms of comparing the pendulum to a spring, this one's kind of a fun one. So if I double the masses, I want to think about what happens to the force and the acceleration. So let's think about the force in the first case, because the difference between the spring and the pendulum is what is the force that's restoring it to center. In the case of the spring, it's a spring force that's restoring it to center, which looks like F equals negative kx. In the case of the pendulum, it's gravity restoring it to center. So if I increase the mass of the pendulum, I do increase the force on the pendulum as well. I don't increase the force on the spring and the mass. So now I have a situation where the spring and the mass have the same force, whereas the pendulum has a larger force. So now that the pendulum has a larger force, right, it's now going to accelerate faster, right, than the mass is going to. It's actually going to accelerate at the same rate as it was before, and it's really the spring and the mass that is slowed down, given that it's now the same force working on a larger mass. So the last of the conceptual problems is really similar to that. So the idea is because I can reason it out from the previous part, right? If the spring is now accelerating back to center more slowly, it's going to take longer. I can also, at this point, write down my expressions for the period. So when I write down the period of the pendulum, right, mass doesn't show up anywhere in the period. If I write down the period of the spring, right, it goes like the square root of mass. So if I increase the mass, then I increase the period of the spring, meaning that the spring now takes longer to return to center, whereas the pendulum is unchanged. Okay, the last of the kind of open-ended problems that we work through in groups. So this is kind of just a mass on a spring, and I know the spring constant, I know the mass, and I know the initial velocity. So I can find the period, right? looking at the same equation I looked at before. In this case, I want to find the amplitude. So this is when I'm looking for the amplitude and I know the velocity, this is a great cue that I want to look at what's going on with conservation of energy. So I can find the total energy given that I know the initial velocity and position, right? So I know at time 0, I'm at the equilibrium position, so I have no potential energy, and I have an initial velocity. So my energy at time 0 is all kinetic energy. So I can use that to find the total energy. The total energy is going to be equal to 1/2 k times the amplitude squared. So the amplitude, right, is going to be around 0.5 meters. The other bit that I need to figure out the x of t is something to do with the phase, right? So it's like the amplitude times the cosine of omega t plus some sort of phase. And so to find the phase, I just really want to ask the question, where is this thing at t equals 0? So at t equals 0, right, my position is also 0 if my position is measured from equilibrium. So I need a phase where when I put it inside the cosine function, it's going to give me 0. So the answer is going to be, right, pi over 2 or negative pi over 2. In terms of whether it's positive or negative pi over 2, I would have had to tell you which way the initial velocity was. So I didn't tell you whether the initial velocity was left or right. So either a pi over 2 or negative pi over 2 is fine. If I wanted to go further and be more precise, I could take the derivative of this to find v of t, and then whether v of t is positive or negative at time 0 would determine whether my delta has a positive or negative sign. So if I had a problem where I needed to figure that out, that's how I would do it. Okay, oh, we had one more problem I forgot about. This is really just kind of the same as a previous problem, just asked again. So friction acting on an oscillator is kind of conceptually identical to what I did before, where I tapped on the pendulum bob that was swinging. So I mess up the energy, meaning that I change the amplitude and the maximum velocity, but not period or frequency. So that's just kind of duplicate.